Hello, um, let me review today data reduction for the USAXS SAXS and WAXS instrument at the Advanced Photon Source. This movie is only for users of my instrument, for those who either came and collected data themselves, or for users who sent me samples through a mail-in or collaboration, and therefore now they have their data. When the USAXS instrument collects the data, it generates a folder with data. The folder typically has a name of month, underbar, day, underbar, and the username, some kind of associated username. Inside the folder are either folders directly, that's an older system, or starting from now, and now is in October 2025. There's going to be a folder called data, may potentially called other folders with a sample 1, sample 2, or whatever. Structure in this folder can be created by user during the data collection, so they can separate their data into a meaningful structure. So here are data, and inside there we have now 3 different folders. One is data underbar USAXS, next one is data underbar SAXS, and data underbar WAXS. USAXS contains USAXS data. That's a unique instrument at the Advanced Photon Source, which uses what is effectively a diffractometer to measure very small angles and can get data up to about 20 microns at high resolution mode, and then extends it down to less than an angstrom all the way in the powder diffraction. We have a data underbar SAXS. That's a data collected over an intermediate range of small angle scattering at relatively higher Q values. And then we have a WAXS, which is also known as a powder diffraction or diffraction. And inside each one of these folders, you will find that you have typically a file with an extension of H5 or HDF or HDF5, something like that. These are HDF5 files containing your data, and then there are also images which you can display, and these will be the images when the sample was collected. So this is a picture of sample 4 when the data were being collected. What we need to now do is reduce these data and put them on absolute scale and everything else. And we do it in Igor using a procedure, which I'm going to demonstrate now. This is an older procedure, which will work for data going back at least 10-15 years and will be kept alive or available into the future. I'm currently working on much faster procedure, which skips many of the steps I'll be showing now. That one will be available probably in January, February as a beta version, and will be much easier. Anyway, so for now, this is a detailed method, and I just started Igor Pro. Then I have installed my packages, all 3 of them, Indra, Irina, and Nika. You need all 3 of them. And that is on a movie I recorded yesterday. You can find it on a YouTube channel. What you want to do is you want to load all 3 packages, USAXS, Irina, and Nika. So if we click on this, we will load, and here we get a USAXS, we get a SAXS and BioSAXS, and we get a SAS 2D, which is the Nika package. We will start in the USAXS package. So we're going to go in here and import and reduce USAXS fly scan data. This is the same procedure for fly scan or step scan, but we have nearly abandoned the step scan a few years ago. But now, due to high resolution mode, it came back. So some of the naming system is a little obsolete at this moment. Anyway, so here is the main panel, which you can see. And on all of the panels in my code, you start at the top and keep going down towards the bottom. And you typically start at the left side of the screen and go to the right-hand side screen. So we start here, select the data path. We will point the code to the data, and I believe I have them on desktop. Oh, it's a wrong desktop. This is the right desktop. So here is the month, day, username. Inside is a folder called data. Potentially there will be other folders. And inside each one of them are all three segments which you collected. So we first collected the USAXS. Let's reduce the USAXS. Now, for every measurement in small angle scattering and even diffraction, you really should have a measurement of the background. In USAXS, you actually cannot reduce data unless you have the background. These samples were powder samples inside a tape. So a proper background measurement is the measurement of the tape. So we collected tape without any powder, call it a tape blank. And if you double click on it, you will now see a curve which has been corrected for all these dynamic ranges of the amplifiers, background subtractions, and everything else. You also see this fit to the main peak profile. So let me explain what this means is. In this case, the instrument has a high resolution analyzer crystal, and it starts and scans the analyzer crystal from a specific angle all the way up to some other angle. It does it actually in nonlinear steps. It starts slightly above the diffraction peak in angle, and then keeps going towards smaller angles. And so what you see here on this screen here in this place, you see that we have a intensity which forms a peak. This is normally the direct intensity of the beam, and in small angle scattering normally there would be a beam stop which protects the detector. In the USAXS instrument, there is no need to protect the detector. The detector can survive the whole beam, and so we scan through it. And then in order to find what is the intensity and what is the position, which is realistically the Q equals 0, we do a fit of a peak, which is a combination of Lorentzian and Gaussian, and so you get this blue curve here. That gives us numbers for maximum, full weighted half maximum, and beam center. These are the numbers which then go in calibration. This is a well-looking data set. Occasionally, you may find out that these are the different ranges. There would be artifacts, like there's a small one in this area here. It's negligible, but there could be an artifact when the dynamic range of the amplifier has changed. In that case, contact the beamline staff and we'll figure out what and how we can fix it. Anyway, so we saved the data, and that has saved the tape blank in the Igor experiment. Next, we're going to process a few samples. So let's uncheck the checkbox process as blank. And we now have here the list of measurements which we processed as blank. By default, it selects, and it gives us this red lane here, it selects the first one which exists. It is a user responsibility to know which blank belongs to which sample. There's no way for the instrument to know. So now we're going to go in and double click on sample 4, and what you see is that we have loaded in a data set, and again we fit it in this top part here. We have fitted the Gaussian, modified Gaussian profile to it, and that gave us again a full weighted half maximum, and beam center. In an ideal world, the sample and a blank after correction for transmission, and this is one of the two transmissions in the system which exists, will overlap perfectly fine in this graph. Out here, we get few choices to do, and I will eventually go through more complicated explanations on those in another movie, but for now, presumably that you have a sample thickness, which would be a number here that actually is provided to the measurement of the data. So when you're collecting data, you need to provide an appropriate thickness. Typically, that would be anywhere between 50 to 100 micrometers for foils, metallic foils, and other things. to millimeters for polymers and other things, and then maybe up to 4 millimeters for NMR tubes, because our instrument typically operates at 21 to 24 kiloelectron volts, so we have a high penetration capabilities. We have measured sample transmissions. So there is a sample transmission. This one is actually measured during the data collection by a photodiode. So before the data collection, we actually collect your transmission. This is the second transmission in the measurement. So one is here and one is here, these two ones. They might be different due to something called multiple scattering. Again, I'll get to it some other time in another movie. So the next thing is, if you want to see what the ranges of the amplifiers, where they are here, you can more or less ignore all of the other parameters here. What can be useful is to de-smear the data. Now, the thing is, this is a diffractometer with a very high angle resolution, but a very high angle resolution only one direction. In the second direction, perpendicular to the first one, for the high resolution direction, we have a slit definition of the beam, and so the data are slit smeared. The code can de-smear the data, which is valid if the sample scatters isotropically. If it is an isotropic scatter, things get complicated, in which case talk to the beamline scientist first. So now what the code, by checking this checkbox here, we can see there is an extension to the data. This red dotted line needs to match the data reasonably well. It generally does. The blue is slit smear data, the green is de-smear data, and what you can see is it basically increases the intensity at low Q. At high Q, the intensity stays about the same. These de-smear data now can be modeled with any other small angle scattering modeling tool. So unless you're using IRENA, which can model data in a slit smear configuration also, or SASView, which I have checked, and it seems to be doing really good models in slit smearing too, you probably want to de-smear the data. When you are happy with the data, you can hit Save Data, and it will generate a graph. Now let me do a few more of these. And you can select them by holding down Shift or Control, and then you can do Process, and you can see how it goes through it. It has a built-in delay, which is down here. That's so you have time to look at the data and realize something might be wrong. Now, those images which I showed you, you can actually see them if you check this checkbox here, Display JPEG Images, and you double click here. You can see the image here. So this is an image of the data set. Now, what we did now is, in a data browser, which is an Igor tool, and if you don't see it in data, there's a data browser here. In data browser, you can see a structure of data which somehow resembles what we have on the hard drive there with the folder for USAXS data. Ignore the packages because that's where temporary data go. Ignore the raw, that's empty anyway. And in a USAXS folder, now we have these folders which represent the data we have just reduced. So we have a folder for sample 4, sample 9, sample 39, and so on. So this way, and they are here in this graph here. This way we have now reduced the data for USAXS. You can go through all of these one after another and reduce them. Next step is we have to reduce the data for SAXS. So we'll kill this thing. We can kill also this. Now that's done using a NICA package. A NICA package is the tools which sit here as a SAS2D. And I have made the system really simple. You go to Instrument Configurations, select the APS USAXS SAXS and WAXS instrument. you get a graphical interface in which you can select, I'm doing SAXS, and then the calibrate geometry is used by staff at the beamline. So what you are doing is you are using the set default setting button. You do it, it will ask you where the data are. And so you need to navigate to the folder with the data, which is the data underbar SAXS, or whatever was your sample name underbar SAXS. And inside are files with a extension HDF, and we can simply double click on one of those and import the data. Next, what we want to do, it puts you here on a tab number 4, and that's because we need the background. So if you right click in this window and say match blank, then you're gonna see only the data which contain a string blank, and you can simply double click on that. So now this is an image of the blank data measurement. This is an image of the data themselves. Then what we can go in here, select the data set and double click on it, and you will get a data set. Now, oftentimes what happens is that the background in some area is actually higher than the background of your sample. There's a long and wide explanation of why that happens. It's a typical problem where your sample contains less of something than your background. For solutions, it often is a solvent. In this case, the tape we used was probably a different one and scattered more for the background than what was the tape which contained the samples. Now there's a way to kind of fix that, because this what happens here, you get negative intensities. So you can actually do a fixed background over subtraction and redo it. Now with this really doesn't fix anything. It just makes all the data positive by offsetting that them slightly higher in intensity. So it prevents the log scale to look ugly, but other than that, doesn't make much of a change in the data themselves. You just have to know that this area here, you have over subtracted your data. So that's how we do this. We can select all the other ones and say process images, and you can see that you are now getting the data here in this range. So that's the second segment. The next segment is the powder diffraction area. Powder diffraction is in the wax, and the procedure is exactly the same as was the first one. We go here. Now you're using a wax powder diffraction, and you're using the standard one. Ignore the other ones because you don't have that. Again, you click SAXS default settings. You go back in data folder, find the wax folder, and double click on any one of those images. Here in this panel here, you have to load in and make sure your empty is in there. They both look ugly, but if you just click on this, you will see that there are some differences between them. And then we come here and double click. Now it takes a little bit longer time because this is bigger image, and it needs to recalculate lots and lots of parameters. But what you can see now, that in here we now have the data extended from the about 1.5 or so all the way up to 5 or 6. Exactly where they get extended, how far, depends on X-ray energy, sample to detector distance, and other parameters on that. If you need to hit or reach specific diffraction peaks, this needs to be optimized before the data collection, not after. And then we can select the other ones and say process images. And we have. So now what happens, we have done USAXS, we have done SAXS, we have done WAXS. We can close this, close, close, close. Now I can show you how the data look like. We can go and say, here is a multi-sample plotting tool. Let's start with the USAXS. We pick on a USAXS and say we want to have sample 4 and let's say sample 9. So this is sample 4 and sample 9 USAXS data. Then we can plot the SAXS data. So that's sample 4 and sample 9. Okay, apply. And you can see that there is an overlap here, and then the data continue further out. And then we can say we're going to overlap also the powder diffraction, and so we have a sample 4 and sample 9. Now, in an ideal world, all of these data would overlap exactly, but it doesn't happen. There are some reasons for it. First thing is I have to get the calibration right during the setup exactly right. That's usually not a problem, but there could be few percent variations. There's a bigger problem is that the USAXS uses about a 1 millimeter square beam because it has a very high angle resolution with a large beam. That's perfectly fine. The SAXS and WAXS are area detector based data devices. And so in order to have a good angle resolution, you have to have smaller beam. So actually SAXS and WAXS may be probing slightly different volume of your sample than the USAXS. Now, that means that the intensity often is offset a little bit vertically up and down. And to do this, to get a meaningful curve, we can actually merge the data together using a specific tool, which is in IRENA. So we go in SAS, which is IRENA, in data manipulation, and we're going to find merge two data sets. In the merge two data sets, we're going to select a USAXS data. We're going to select the USAXS data here, and here's our sample 4. In here, the SAXS and WAXS are both using what is called QRS. So if that is done, so we come in and say SAXS, and now you can see we have a S4002, and then we have S4002, and the 27030 is the way the NICA denotes in which direction and how it reduced the data from the area detector. Because on the area detector, it depends also what is the direction, because you can go up, left, right, down, and then it depends on the range of data which you are selecting for that. Right, so if you double click 1, double click 2, you realize there's an overlap here. You can select the range of data. Typically, I will select data which are not starting at the very, very beginning. So I will not select the very few typically high error bars, uncertainties, points at low Q. I will usually not select that many points at high Q. And then you can pick here merge method. Description is in the manual. You can do typically the first or the second one are good. And now we're doing SAXS, so we have a SAXS is a log display, and you can do process. And what it does, it optimizes two parameters. It optimizes the SAXS data set height, so it scales it. And in a USAXS, because USAXS is very low intensity, there's some flat background in it, it tries to subtract the flat background. So it optimizes the background of data set 1, which is the USAXS, and a scaling of the data set 2. And you can, if you like this, you can go in, select the points, it will do the fitting, and it will merge the data. At this moment, it created USAXS data called USAXS S4002 underbar MRG, which means it's merged together. If everything works well enough, you can actually select the range of these, and then you can select process as a sequence, and then you can try processing automatically. and you're done. So now what we have, if we go back to multi-sample plotting to go to USAXS, we actually have the merged data. So if we click here, you can see that the data agree with the USAXS all the way, but then actually go down and agree with the SAXS. So now we have one curve which covers the range from 10 to minus 4 inverse angstroms, which is about 6 microns in sizes, and we get all the way up to above 1 inverse angstrom here. So that's about 0.6 angstroms or so. Anyway, 6 angstroms. Now it is theoretically possible to merge the data together. So if you come in here and reselect the USAXS, it will refresh what you have available, and then we can go in and we can say wax, and that one has a different letter here, so underbar C. It doesn't matter at this moment, but you can go in, put it back in test mode. That's the original data. This is the data for S4. And then typically I would leave out the background because now the SAXS has very little to no background. I would just scale the data set 2, and you need to make sure there's an overlap of the data. So, and then you say process. And if you process, you can see that it had to scale the data 2 up by 5 or 6%. So that's pretty good. And so if you say save now data, you actually have now data which are still USAXS, but they are underbar MRG that added the first SAXS, and the second MRG means you added the wax. So then you can go in here and you can select with Control or Command gonna go with the merge mode, save, and process a sequence. Okay, so now what we have is, come here, and we're gonna redo it in a USAXS folder. And now we have these double merged data sets. Let's create a new graph. And if you look on it, now you have data which extend from 6 microns all the way up to less than a 1 angstrom, or typically close to 1 angstrom. So you have ultra small angle scattering here. You get a typical small angle scattering here. So you get, 100 nanometers, 10 nanometers, 1 nanometer. And then oftentimes you have diffraction peaks in this area where most of your powder diffraction area are. All of that can be collected on the instrument within probably about 2 minutes. And the data reduction I just walk you through can be done within, a minute or 2 per sample too. So this is a detailed data reduction. Things will get easier in the future. But if there are any failures or any unusual events, this method will be used anytime into the future. And again, this procedure, the code currently available, can reduce data at least 10 years back, and it should be able to reduce data for both fly scanning on USAXS as well as step scanning on USAXS, and collect it with any area detector we ever had for SAXS and wax. And that's about it. If you run into problems with this code, please send me an email and let me know, and I can look at it and we can evaluate what's wrong and fix any potential bugs. Okay, thank you, and have a good day.